Now that we've completed our virtual breadboard circuit, it's time to actually lay out our PCB. If we click on the tab along the top, we can switch to the PCB view. Now this is going to show us maybe a little bit of a mess of the different components that are involved in our circuit, right? And they may be overlapping. If you mouse over the icon, you should see this gray selection be made visible, and you can click and drag to reorient or reposition these components. You can also use the rotation tools or the square brackets like we did before to also do rotations. Now, what we see between the components are what are called air wires. They basically are saying that this connection needs to be made with a real trace, a real copper connection. Now, because a bunch of things are connected to the same components, not exclusively, but we've got parallel branches in this circuit, right? A lot of things connect to ground, a lot of things connect directly to 5 volts, or our input voltage. There may be more than one way to draw these connections. And you may notice that if you drag a part around, the air wires may change. The suggested air wires will depend on the proximity of a component to another one. So for instance, if my resistor is up high, you can see that this resistor is going to be ultimately connected to one side of the LED, pin 3, and the other side of this capacitor, right? But if I change the orientation, it doesn't have to travel in that way. All 4 of those pins were connected to each other. So depending on my placement, I may be able to be clever with my routing. Since this is a single-sided printed circuit board we're trying to make, our one constraint is that we can't have any overlapping lines. Now, it sure looks like I've got a lot of overlapping air wires right now, and I do. And that's where we have to start untangling things. Certainly, anytime we have a component, like this resistor would be a perfect example, that its leads are crossing with itself, I can uncross them just by rotating the object. Right? If I rotate it, it's going to unwind those 2 components. Right? And so what we want to do before really anything is just to play around a little bit with the air wire locations. And the air wires won't be perfect, but we want to try to untangle things so we have less overlaps. Right? I think this would actually be a good example of how we could problem solve. Here I've got a couple overlaps. I've got the purple overlapping with the green, and I could solve that by rotating this object one time. But then I also have this green wire wants to overlap with these other green wires. But we notice that also connects here. Now, let's see how we can actually create a trace. If I want to put a trace in place, I just have to drag a line, just like a wire is created between 2 connections that had an air wire. And once I'm done that, a trace will be created, and that air wire will disappear, saying that we've routed it. We've made that route already. Now, if I want to, let's say, bypass the overlaps, there's all sorts of overlaps happening here. I know that I want this connection to get all the way up to the top of my LED up here. But that is also connected here. So, which is really, this is part of my battery connection, right? This is the ground that we're connecting here. I could bring the ground, oh, I don't want to grab the air wire. I'll undo that. I want to grab the pad. And I'm going to make a connection all the way up to the ground here. And because that was a valid connection, we'll see that the air wire has gone away. Now this trace is still a little bit suspect. It could travel underneath the resistor itself, because that's not where we're soldering it in. But it would interfere with a wire that we have yet to make here. Although whether or not we want to do this actually just depends on how we're going to solve the problem. Right? I could run this trace could run outside here. So this may not be actually the worst solution, but certainly I don't like how close this is. It's running over top of the pad. So I might rotate this a little bit to free things up. And probably the way that I'm going here may introduce some problems, right? I can see these 2 components want to be close to each other, which wants to be close to this, which wants to be close to the bottom half. So probably a better design would involve maybe bringing my 5/5 timer up a little bit, bringing these components all down so they can be close to each other. Maybe I'll bring this component over this way. And you'll see that actually as I bring it down, it's going to change the air wire to the bottom half. So I think I'm more or less on the right track here. And I could create some traces for the more obvious ones. And drag. And this one, we're going to go over to the resistor. I think I won't actually solve the problem here. I've done one, and I have a PCB design that's ready to go, ready to mill. And I think one of the interesting things here is that there's more than one way to solve it. So certainly, I'd like you to try. If you need to, you can probably take a look at my design and get some ideas there. But it's really a puzzle that you can solve. Now, there's a few things, technical things that we do need to do. One is for each of the traces we create, the standard thickness of the trace is 24 mils. Because we're cutting this out of with our CNC mill, it is quite common that if our accuracy of the mill isn't perfect, we're going to carve too much and the mill is going to get skinnier. So to compensate for that, every trace you make should be a 48 mil extra thick trace. Knowing that we aren't going to get to keep it at 48, when we run the test, we can use some calipers and see how much is actually left. But every single trace needs to be set to 24 mil. We need to be careful to make sure that we don't have traces overlapping. And if you're getting further into PCB design, what you'll also see, and maybe I'll just make one more trace to illustrate that, is that I can click and drag to create elbows just like I can in the breadboard view. And right angles, hard angles, are actually less effective in PCB design. Because of the type that we're manufacturing, I think we can get away with some angles, but really 90 degrees are the worst. So if you can have them be bent at a different angle than that, a less sharp or a more obtuse angle, that's going to give us a higher success rate. Certainly if you look at professional PCB design, you'll see a lot more curves in the traces. I find that making curves and editing them in fritzing isn't super intuitive, and maybe I just need to spend some more time to get good at it. I'm not sure. But the best solution is actually to introduce curves if you can, for any of the times that we're changing directions. Straight lines, of course, are great. And in my solution, I ended up making it all polygonal, but just trying to avoid right angles wherever possible. Okay. The last thing to consider, so you'll have some solving to do, and once you've made your traces, you can still move the components around, and you can always adjust, or either add new traces or adjust the path of the traces. But once you're done the design, the other thing to think about is the actual footprint of the PCB. Now, if I was sending this off to a fabrication shop, probably I would just make the footprint a little bit bigger, or like the overall contour of the PCB just a little bit bigger than where all the parts can fit on it. Maybe my potentiometer is going to fit in here. Maybe the speaker is going to fit in here. Some of the parts you need to think are going to take up physical space. The potentiometer is a bit of a bulky thing, so it will take up some space. But because you're carving this on a particular CNC router, the Carvey, that has a part of the material that we will place into it won't be able to be carved because of something called a smart clamp. And that's what it uses to detect where the top surface of our object is, which is important. If you don't know where the top surface is, making a very, very shallow cut in an object isn't really possible. So essentially, the first inch or so of our object or of our PCB material won't be carvable. So to compensate for that, what we want to do is we're going to take the overall contour of the PCB, and I want to pad it by about an inch. Now, if you look at the bottom, down right about here, it will tell you the current X and Y position. So if I look at my leftmost through-hole component, this says X is equal to 1.1 inches. If I move to the left, it's getting smaller and smaller and smaller. So I want the outside of my shape to be at about 0.1. Right? I need to pad it by about an inch. Okay, so if I move this over here and check that again, that's 0.17, so maybe just a tiny bit more. That's 0.05. That's 1.1, so that's just greater than an inch. And that's exactly what we're looking for. And then what we want to do is do that on all of the sides. So we can try to just expand. Maybe I'll zoom out a little bit. Just try to make that so it's an even border all the way around. And this would just be the outside most thing of the circuit, whether it's a trace or a through hole. And we just want to make sure that we have an inch of padding on every side. And of course, please save your work regularly as we're going through this. Once you're done, we want to, well, we'll save a fritzing file so you can always get back into it. But if you click this little down arrow and say you want to export an extended Gerber RS-274X, this is going to basically ask you for a folder. So I could say this would be a demo export. You just point to the folder, select the folder. It will take a second to export, and then if I were to navigate to that demo export, it will generate a number of Gerber files, which we'll use in the next step to create the G code for the router to mill out our printed circuit board.